All right, hey, more on our fluid dynamics. Number 35 looked like a good one. It says the arterioles, which are small arteries, lead to an organ. They constrict in order to decrease flow to an organ. Well, let me stop right there because the physics part of this is if we have, this flow through here, we said that there would be a drop in pressure. So if we call the pressure down here and the pressure over there, in lecture, we said that if you took the drop in pressure, so P2 minus P1, it would be equal to 8 times the viscosity times the length, and then over, oh, wait, I think I'm missing something. 8 times, the flow rate, yeah. So it was 8, so the pressure drop was proportional to the flow rate, the length, and the viscosity. That makes sense. And inversely proportional to, and it's r to the 4th power. And I always find this an amazing number and then your author did this without proof, and rightfully so. It's a little beyond the level and the intent here of this class, but we did it with the idea that we can actually use this. Oh, and then be a negative. Okay, so that would be our drop in pressure. Also, I should point out that the author kind of wrote this the opposite. And I think that's kind of confusing. They put a 1 here and a 2 here in the second half of the chapter. And in the beginning part, they called where the water goes to number 2, or the fluid number 2. And then later on, they said where it goes is number 1. So not sure why the switch in thinking. In this case, I don't know if it really matters because we're just going to do the pressure drop. And so we're just going to get an absolute value and see what, that does. In fact, what's the question say? By what factor did the radius change? Okay, so I guess I would say we're not going to really calculate the actual Q value. Well, we're just going to kind of put this and say the blood pressure is exactly the same. Well, let me continue on here. But as far as the physics goes, that kind of covers it. But as far as maybe the life science goes, I always find this quite fascinating that your body and other living organisms can then make that contract. And of course, if you do for the same pressure, so assuming your heart doesn't pick up the pace there and pump harder, but for the same pressure, this narrowing of the artery really then reduces the flow. So if you reduce R and it's raised to a factor of 4, you're going to really be able to reduce the flow rate for the same pressure. And so I guess the first thing that comes to my mind here is kind of your hands and your feet and your ears. If it's cold, your body will really constrict those and keep the blood from going to your hands and your feet and your ears, because that's where you have a lot of surface area and you can lose a lot of body heat. And so your body just naturally says, okay, let's start shutting those down. And so you just, you feel it in your fingers and your ears. Actually, in the reverse is also true, that if your body's trying to get rid of some extra body heat, it can really just change the radius a little bit. That changes the flow, especially to the ears. The ears lose a lot of heat. It's surprising. And you can really then dissipate a lot of heat, besides sweating, but outside of the body, just by getting that blood flow to the ears. In fact, now that I mention it that way, I'm kind of thinking of, if you were to have 2 elephants it's easy to tell an African elephant from an Asian elephant because of the size of the ears. The African elephants live in a much hotter environment, and in order to dissipate that heat, they run the blood through a much bigger surface of the ears. And so the Asian elephants have, I don't know if I want to say tiny ears, but they're smaller than their head, whereas the African elephants have that giant ear. Okay, but I digress. And there's other animals. In fact, as I read this and looking ahead, the last sentence says penguins do this when they stand on ice to reduce the blood flow to their feet. And again, same idea. Reducing that blood flow would mean then they're going to have a loss of heat out their feet. And so it makes it possible then to stand on ice without then losing all your body heat and needing a lot more energy and fuel to get through the winter as you're standing on ice. And anyways, here's what I guess I'm getting at. If you think about this in terms of maybe before the arteries contract. And so let's see, constricts in order to reduce the flow. You can shut down the organ if you reduce the flow to 1% of its original value. By what factor did the radii change? So let's do this. Before, okay, the artery reduces, I would have a flow rate divided by pi, and let me call this R1 to the fourth power, okay? And that would be the absolute value of the pressure difference as it flows from going into the organ, the hands, or the foot, the ear, whatever, and coming out. Now, if there's a contraction going on, okay, you're still going to have the viscosity of the blood. You're still going to flow through the same length. But this number drops down, and then they said 1%. So that's a low flow rate. I'm kind of concerned about keeping whatever this tissue is alive when you drop down to only 1%. But I can't really answer that question. I'm going to take this as that's, still valid to keep your feet tissue alive for the penguins or to keep your hand tissue. Anyways, there is then going to be some new radius. So we call it radius 2. And both of these equal the same pressure drop. Okay. And so what I'm getting at then is we can set these equal to each other. So 8 eta L Q before the contraction, pi R1 to the fourth, must equal 8 eta, and remember 8 is the viscosity, times the length, times then 1% of the original flow rate over a pi times R number 2. And so after it's constricted here. So notice that the 8 really doesn't matter. It cancels off. Notice also that the viscosity really doesn't matter. Notice also the length doesn't matter. The flow rate, again, doesn't really matter. The 1% is what's important, and the pi. And so if I then, why don't I move this over to this side? So this would be R1 to a 4 over R2 to a 4. And then I'll move this 1/100th over. So this is 1 over 100th, which is 100. And so now if I say the ratio raised to a power of 4 is then equal to 100, I will take the fourth root of both sides. So let me take, how do I want to do this? I guess I'll just raise it to a power of 1/4. How about that? I was just going to take the square root twice. but I'll just raise it to 1 over 4. How about that? Okay, so to a fourth power gives me about 3.16. So 3.16 would be this ratio. And I guess I would then say something to this effect. Let's see how they would want it. See, R1 is bigger than R2. So 3.16 times the smaller radius is then equal to the bigger radius. I suppose if we wanted to do it the other way around and say how much is number 2 compared to number 1, we would say number 1 is then reduced by 3.16. Which has got to be like a 0.3 or something. So 1 divided by that last answer. Ooh, 316. That can be confusing. Okay. So starting with the big radius and taking about 32% of it, we now get the smaller radius. Or the other way around, we take the smaller radius and make it bigger by a factor of 3.16, we get the bigger one. So we could say it's reduced by a factor of about 3.2, which is about 32% of the original. All right. Nice. Was there a part B? No, it just says by what factor did the radii contract by. Okay. All right. Hope that helped.